Hello everybody, welcome to my YouTube channel Easy Mathematics. In this video, we come to know about absolutely convergent and conditionally convergent series. But before starting the absolute convergent and conditionally convergent, we should know what is the mixed series or positive and negative term series. So, for the mixed series, I hope you can get the idea that it is the mixture of the positive and negative terms. If in a series there are infinite number of positive as well as the infinite number of negative terms, then the series is called the mixed series. So already we have such kind of mixed series taken as an example. You can remember the alternating series. So alternating series means consecutively positive negative these terms are there, then it becomes the alternating series. So in an alternating series there are infinite number of positive terms as well as the infinite number of negative terms also. So this one is the alternating series, which is the example of a mixed series. Now oscillatory series, like here it is +1 -1 +1 -1, this one is an oscillatory series. This one also we can say as the mixed series. It is not necessary that it should alternatively positive or negative, then only it is a mixed series. But if in an entire series, if there are few terms positive, after that few terms negative, after that again few terms positive, then negative, there is no parity. That means not necessary that if 10 terms positive, then next 10 terms should be negative. That is not mandatory. But the thing which is mandatory is the infinite number of positive as well as infinite number of negative terms are there, not in a proper order, then it is a mixed series. That is the mixture of the positive and negative terms. If we have alternatively positive negative, then what to do, that we have know from our previous video, which is the alternating series video. There we come to know how to solve or how to verify the nature of such kind of series. But if you have the mixed series, then we have two type of things available. One is the absolutely convergent, another one is the conditionally convergent. Now we should come to know what is the absolutely convergent series. An infinite series, here an infinite series summation an of real constants is said to be absolutely convergent when the series mod of an, that means all the terms, whatever the terms are there in the given series, all have taken under mod, that series is convergent. Then the series is called the absolutely convergent series. I hope you can guess from here that whatever be the series given, it is a mixed series. That means few terms negative, few terms positive, and when we take the mod of each and every term, then the entire term becomes the positive. So that this one also we can say the positive term series. What is positive term series? That already we know in our previous video. So for absolutely convergent series, whatever be the series is given, we take the mod of each and every term. After that, this converted series, if we will find out that it is convergent, then we say the series is absolutely convergent, otherwise not. Now it is the conditionally convergent series. So what we mean by the conditionally convergent? An infinite series of real constants is said to be conditionally convergent if the series summation an converges, but not absolutely. What does it mean? That any mixed series given, this one is convergent, but if we take the mod of all the terms, that means the absolute convergency, if we are going to test, then we will find out that the given series is not absolutely convergent, but the original series is convergent and its mod value series is not convergent. If we will find out such kind of things, then we say the given series is conditionally convergent. So let us try to understand this conditionally convergent and the absolutely convergent with an example. So the example is prove that the series x minus x square by 2 plus x cube by 3 minus, in this way this is the infinite series, is absolutely convergent when mod x is less than 1 and conditionally convergent when x is, that is mod x is equals to 1. So we are supposed to prove this series is absolutely convergent when mod x is less than 1 and conditionally convergent when mod x is equals to 1. So let us verify this one. Initially, for the given series, here the series, if we write in this format, then un is what? If we just verify the series, then we will find out un is equals to, first of all, regarding these terms, it is x to the power n by n. Now to adjust these positive negative terms, we should consider here minus 1 to the power n plus 1. So that now if we substitute n is equals to 1, we will find out the value is x. When we substitute 2, we find out minus x square by 2. When n is equals to 3, we find out plus of x cube by 3, and in this way we will find out this entire series. So un is the representation of each term for this given series. After getting this one, for absolute convergency test, what to do? We at first take the mod of each and every term. If we take the mod of each and every term for this one, then we will find out this one as mod of un is equals to mod x whole to the power n divided by of n. Now what to do? We have to verify that this series, this converted absolute series, is convergent or not. For that we take the D'Alembert's ratio test. So un we have, so mod of un plus 1 also we can easily find out, and if we take the ratio of these two and take the limit as n tends to infinity, then we find out this limiting value is mod x. Hence by D'Alembert's ratio test we say the series is converges when mod x is less than 1 and diverges for mod x greater than 1. So we can say from here that the given series is absolutely convergent for mod x less than 1. So just observe from here that it is very simple. After conversion of the given series in the absolute term, after conversion of this series in the absolute term, what we will do? We will find out the series of positive terms. That means all the terms becomes positive. When all the terms become positive, then whatever the properties we come to know about the series till date, that we should apply. So as here the un is equals to mod of x to the power n by n, so that we apply the D'Alembert's ratio test first to verify that we are getting the positive response or not. So after applying the D'Alembert's ratio test, we will find out that the given series is convergent when mod x is less than 1 and divergent when mod x greater than 1. When definitely mod x is equals to 1, this test fails. So that we have to go for the further analysis. So according to this D'Alembert's test, we can say the given series is absolutely convergent for mod x less than 1. When x is exactly 1, that means when mod x is equals to 1, then what happens? When mod x is equals to 1, the given series reduces to 1 minus 1 by 2 plus 1 by 3 minus of 1 by 4 in this way. So for this series, the nth term is minus 1 to the power n plus 1 by n. Now if we consider the absolute value for this series, then what happened? Then we will find out this one is the series of positive terms, which one is an HP series, which one you can say a HP, or you can compare with the P series also. This one is a P series where the P value is 1. So P value is equals to 1 means the given series is not convergent, but it is a divergent series. Hence the series is not absolutely convergent when mod x is equals to 1, as the given series is an alternating series. I hope you understand that this series is the alternating series, as consecutively positive negative terms we have. So as the given series is an alternating series using Leibniz theorem, we may conclude that the given series is convergent. I hope you can remember the Leibniz test. So for Leibniz test, at first we verify that un is greater than un plus 1 or not. Here our un is 1 upon n. So definitely u of un plus 1 is 1 by n plus 1, which is from where we can say that un is definitely greater than un plus 1. And when we take the limit n tends to infinity un, then definitely this value is 0. So both the condition for the Leibniz theorem will satisfy. Hence we can say the given series is conditionally convergent but not absolutely convergent for mod x is equals to 1. So that we can say the given series is not absolutely convergent. Now let us do one more example. So here the series is, examine the following series for convergence, and the series is 1 by 2 to the power cube plus 1 by 3 to the power cube into 1 plus 2 plus 1 by 4 cube into 1 plus 2 plus 3. In this way it will progressing. So here again un is equals to minus 1 to the power n plus 1, and here it is 1 plus 2 plus 3 up to n, and it should be n plus 1 whole cube. Now if we simplify, then we will find out this one is equals to minus 1 to the power n plus 1 into n divided by 2 into n plus 1 its whole square. We just write down its formula, which is n into n plus 1 by 2, and after simplification we will find out this one, which we can write as minus 1 to the power n plus 1 an, where an is equals to n into n divided by 2 n plus 1 its whole square. Now from here we should find out an minus an plus 1. If we do so, and after simplification we will find out this value is greater than 0 for all values of n greater than equals to 1. So from here we can say an is greater than an plus 1. That means the given series is a decreasing series, and not only that, if we take the limit n tends to infinity an, then this value becomes 0. So by Leibniz rule we can say the given series is convergent. So the given series, given alternating series, is convergent when it is given like this one. Now we should verify for the absolute convergence of this series. So when we consider the absolute convergence, that time we have to take the mod of un. So when we take the mod of un, that time we will find out our un is equals to n divided by 2 into n plus 1 its whole square. So after that, observe this term. Here we will find out that here in the numerator and denominator it is n and 2n plus 1 its whole square. So the difference of the power of n is 1 here. That's so why, as the differences are exist in the power of n in the denominator and numerator, that's so why we should use the comparison test to verify that this series is convergent or not. So for the comparison test, we should consider our Vn as 1 upon n. Yes, because if we consider Vn for comparison as 1 by n, so that we will find out that here when we substitute un by Vn, then in the denominator and numerator both the power of n should be equal. So when we substitute Vn is equals to 1 upon n and then apply the comparison test, then limit n tends to infinity mod of un by Vn is equals to this one, which is limit n tends to infinity n upon 2n plus 1 its whole square into n by 1. So if we simplify and take the limit, then we will find out this limiting value is 1 upon 2, which is not equals to 0. So we will have Vn is equals to 1 by n, which one is a divergent series we know. So being a divergent series, so Vn is a divergent. Here this one is a non-negative, that means not equals to 0 term, that means the finite limit exists, so that we can say un is also divergent from the comparison of Vn. So thus we can say the given series is conditionally convergent and not absolutely convergent. So from here we can observe one thing which you can say as a formula or theorem also, that an absolutely convergent series is necessarily convergent but not conversely. That means any series is given, if the series is absolutely convergent, then definitely the series is convergent. It is the do by yourself question for you, and the question is that test the following are absolutely convergent or not. And the first series is summation of n from 1 to infinity minus 1 to the power n minus 1 divided by 2n minus 1. This is your first example. And for the second one, it is summation n from 2 to infinity minus 1 to the power n divided by n into log n its whole square. So these two are the questions which you should do by yourself, and its answer should be right in the comment box of this video. I hope you understand what is conditionally convergent and the absolutely convergent series, and you like this video. We will do our next video for the power series. Till that, you keep watching, and if not understand, then write me in the comment box also whatever the doubt you have. So thank you all. Have a nice day.